All right, a question I've gotten a few times from students is, hey, I know calculus, right? And I know that the area under a curve is just, I just need to find an integral to solve that. So why is it in statistics all of a sudden now I have these tables to find that area? And these tables really limit me because it only gives me 4 decimal places. Or if I'm trying to find the corresponding z-value, it only gives me 2 decimal places. So, what's up with that? And how can I do better, right? Quick answer to how do you do better than 4 decimal places or 2 decimal places is to use a computer program such as Excel. Excel can give you a better approximation to what the exact value is, but finding the exact value is actually we cannot do it because there is no closed form solution for this area. All right. So that that's basically what I want to talk to you about in this video. How do we use Excel to get better approximations than the table, and why is it that we can't just solve this using a closed form integral? Okay, so let's start with how to use Excel. We're gonna start with how to use Excel to get better approximations. So suppose I want to know the value of z. So I want to know a z-value for which this area marked in gray is 0.975, right? So the probability that z is less than whatever that z-value is, that's why I want to figure it out, equals 0.975. And we use the table, we would look for 0.975, we would find it here, and we'd say, okay, 1.96. So that z-value is 1.96. And how do I do better using Excel? How can I find more decimal places, a better approximation to the exact value? Well, I can go to Excel, and in this example, basically I'm doing like an inverse function of this normal distribution. So I would type in equals norm.s, S stands for standard normal, oops, I misspelled that, norm.s.inv, and then I'd give it the probability that I want, which is 0.975, close the parenthesis, and there I get more decimals, right? And so this is a way to avoid that limitation of only having 2 decimals here in the normal distribution curve. Or sorry, in this standard normal table. Okay. Also, suppose, now let's do another example. Let me use a different color. Suppose I want to find the probability that z is less than, let's do 1.9553.2. Okay, and I want to know what is this. Now, if all I have is the table, all right, I'm going to have to round that. If all I have is the table, I'm going to have to do 0.96, right, because that 5 will round that up, this other 5 to a 6, and then I would get my answer as 0.975, right, because I would go to 1.96 and then I'd be in the same position I was before. But I can use Excel and do better. Okay, Excel, I would type in equals norm.s.distributions. This is dist, and then I would give it my z-value, which was 1.95532, and then I would say true for cumulative. Okay, and I'd press enter, and I get 0.9747. So you see, the answers are the same using the table and using Excel. It's just Excel will give me more decimals. All right. Okay, so why is it I'm just calling these approximations? These are not exact values. Even when I have more decimals, they're not exact values. What's going on? All right, so to understand that, we need to remember our calculus, and remember that the area under a curve is basically what we're talking about, and that's basically an integral. Okay, so what is that curve? What is the function of that curve? Well, for a normal distribution, I'm going to use x to indicate that that's any normal distribution. This is the function. 1 over 2 pi sigma squared times e to the negative x minus mu squared divided by 2 sigma squared. Right? And so for the standard normal distribution, z instead, so now I plug in z for x, we have sigma equals 1 and mu equals 0. So that's, by definition, that's what standard normal is. So this function becomes 1 over square root of 2 pi, right? I just plug in 1 there for sigma. And then e to the power of minus, so instead of x, it becomes z minus mu, which is just z. Sorry, I actually don't need a parentheses there. Z squared divided by 2 times 1, which is just 2. Okay? All right, so this is my function. Okay? So, like, for example, if I want to solve this one, let's go down here. Actually, sorry. Not that one. If I want to solve this one, right? Let's go down here. Basically, what I want to know is what is this area when the cutoff is 1.95532, right? That's basically what this probability statement is asking. What is the area behind 1.95532? Well, how would I do that using what I know about calculus? I would say from negative infinity, I would integrate from negative infinity to 1.95532, and I would integrate my function of f of z. Right, so I can pull out this constant, 1 over square root of 2 pi, because that doesn't involve z. And then I'd have e to the power of negative z squared divided by 2 dz. Okay, so now, you know calculus. So now just solve this. Okay, this is what you need to solve. Okay, and this is where you'll run into a problem. Because if you try to solve this, this integral, it looks simple enough, right? But remember how to integrate when you have e to the power, you have negative z squared. You go ahead, I highly encourage you to try. You will run into problems, and so that's what's going on here. There is no closed form solution for this integral, which is why we have to use approximation methods to solve this. Okay, so every computer program out there is basically using different methods of solving this integral, but there is no closed form solution for this integral. Okay.